Now to some of the use cases. Before I continue, I'll answer some of the questions which I think are relevant for everyone. Again, we'll definitely have time to answer the questions. I'll promise to answer every question that I can at the end of the session. The first one I've already answered is how far away could the display be from the unit? Again, we've tested that up to 20 meters with a standard Ethernet cable. Can the inverter rely on one power source only, the PV without AC or battery? Yes. Again, that is something we don't recommend. You can work with only PV and no AC and no battery, but that would be an inherently unstable system because there's just no storage anywhere. There's no alternative energy sources. So all the inverter can do is turn off if your PV power is lower than your load power. So it would work, but we don't necessarily recommend it. Then whether the AC source switch, that's the one I've showed before. Oops. The switch right here, whether that can be controlled by the inverter. Well, actually it doesn't need to be, because if we take a scenario like this, then typically the genset is only going to be like our last resort. We're only going to want the generator running if PV fails, grid fails, battery's empty. That's when we start up the generator. And what we do is this source selector, which is basically just a relay, the coil of the relay will be powered by the grid. So what that means is when the grid is active, the relay will always be switching the grid to the inverter and the generator will be disconnected. And as soon as the grid fails, it will flip over to the generator side. It doesn't mean the generator has to start. It just means that now the AC path would be towards the generator. Now the inverter, for example, would keep running, would maybe discharge the battery at night, for example, because there's no PV coming in. And then at some point you can use the relay on the inverter itself to turn on the genset when you really need that power. But you've already done the switching beforehand simply because of your logic up here. So use case number 1 of 7. This would be a classical off-grid environment where you don't have an AC source from the grid at least. You can have a generator, which is optional here, and PV, which is optional. Obviously, you're going to need one of the two because otherwise you're just discharging a battery. You need a power source of some kind, but it can be either one or the other. Now in this scenario, again, it would theoretically work without a battery, but we strongly recommend using a battery in an off-grid scenario. So the benefit of this compared to buying an MPPT charge controller plus buying an inverter plus if you're using a genset here buying an AC charger is that obviously you're getting all this functionality in one package in the AnyGrid PSW-H. So you have a vastly simplified system and much lower cost than buying each individual component. And another derived advantage of that is, of course, you don't have to coordinate communication between multiple units, because we'll see later you can use multiple AnyGrids which communicate with each other. There's no programming required for that, but you don't need to coordinate the MPPT from one company with the inverter from another company, etc. Then we have the use case number 2, which is a on-grid scenario with battery and PV. So we have PV again. This time, instead of a genset, we have a public grid. That's our AC source. We're using a battery, and we're using our AC loads. Now, it's up to you if you want to use solar or grid as your priority. I'm sure that in 90+% of the cases, solar will be the priority because, of course, once you've invested into a PV system, you're going to want to use that power. But you could also decide to use the public grid if there's a good reason for it. Maybe the public grid isn't actually a public grid. It might be a different inverter and you want to prioritize that, for example. We're giving you all that flexibility to choose whichever you want as the priority. And then even if you have a real excess of energy, so if your battery's full, your loads are covered, and you still have a few kilowatts left over, then you can push that power back into the grid if you activate the grid feed-in and if it's legal in your area. Now, the benefits of this is that, of course, you save electricity costs from the grid. That's typically the main reason to to build up such a system is to use PV power for your loads to offset some of the power costs from the utilities. But at the same time, you're basically getting an uninterruptible power supply for free, because I think it's very frustrating for a lot of people that are using grid-connected inverters that only function if the grid is there. People get frustrated because they've invested into PV modules and a battery, which are basically the two critical components along with the inverter. But if the grid fails, they're still sitting in the dark, even though their battery might be full and the sun might be shining, or just one of the other. So in this case, that's just not going to happen, because if the grid fails, that's fine. The inverter's simply working in off-grid mode. You won't even notice, because that 10 millisecond switchover time is virtually unnoticeable. And it certainly won't annoy your computers or anything connected, in the sense that anything would turn off. And here too, if it's legal, like I said, you could inject any excess energy into the grid. Use case number 3, you might not have any solar at all. You might be maybe even in an apartment where you cannot install solar, or you just want a big uninterruptible power supply. You don't want a small 500 watt one for just your computer, but you know, you might have a lot of machines. You might be a business. You might want to have your whole home. Basically, you know that your power might fail an hour every day. You want to make sure that you just can keep operating your home just from the battery. So in this scenario, of course, the public grid is your only power source. So when the grid is available, then you simply use that power to charge your battery. And as soon as the grid fails, then you're powering your loads off your battery. Use case number 4. We have an on-grid scenario with PV, but this time with no battery. Like I said earlier, batteries are obviously an important cost driver, and in some cases, it's just more economical to build a system with no battery at all. So that's what we have here. The battery's missing on the bottom left. So in this case, the PV power is going to be your first priority. So let's say you're pushing 4 kilowatts from the PV side, and you have a 4.5 kilowatt load. Well, then the 4 kilowatt is going to come from the PV side, and the missing 500 watts will be added from the grid simultaneously. Here too, you can feed into the grid if it's legal in your area. And well, this is basically equivalent to a grid-tied inverter. The big difference is that the power actually flows through the inverter unit. So taking my same example as before, I'm using 4.5 kilowatts here. The 4 kilowatt is going through the unit from PV and also through the unit from the grid. Now, the advantage of the power flowing actually through the unit, as compared to a grid inverter where it's not flowing through the unit, is that I don't need any external energy meters, because it's all integrated into the PSW-H. It's already measuring the power that's coming from the PV side and the power going to your loads. So the benefit here is that you don't need to invest in batteries, but you still have that flexibility for later, and that you can still use the PV to offset your power costs from the grid. And again, that you can have that flexibility for later. If you do add a battery, it could even be a smallish battery, which, you know, you could reduce the charging and discharging current as required to not to upset the battery. So you're very, very flexible that way. Use case number 5. This is the full-blown one I showed at the beginning of the session, where literally every port is connected to something, and in fact the AC side is even connected to 2 AC sources, the AC input. And this is like, well, if you have everything, you have a grid, you have batteries, you have PV, and if everything, you know, fails and it's night and I don't know, you have snow on your roof and the grid fails, then you still have your generator as a backup to power the whole thing. So this really brings together all of the features of the AnyGrid series. Now, use case number 6 and 7 are both fuel saver use cases. You can already see in red that we require a certain firmware version for that. It's something we've just implemented. All the units manufactured since December will have this firmware update. You can obviously easily see the firmware version on your unit through the display. If you find that you have a lower version than that and you want to use this use case, then please just contact our support and we'll provide you with the software updates to get that firmware version. So this fuel saver scenario with no battery means that you don't have a grid, but you do have an AC source, a genset of some kind, and you want to use PV to reduce your fuel consumption, thus obviously the name fuel saver. So this is quite typical in large industry mining operations, for example, where there's no public grid out there, but there are a bunch of gensets powering your equipment, or you might have a hotel in the middle of nowhere where you want to keep the generator running all the time, but if you do have PV, then of course you want to reduce your fuel costs as much as you can. So that's what we do here. The benefits are, of course, fuel savings. That's the main benefit. Then we have less strain on the generator on average, because, of course, if during the day we have PV power, then the generator will simply have to work less hard. It will only have to provide a much smaller portion of its nominal power as compared to not having PV. And therefore, we probably have longer service cycles and lower maintenance costs. Of course, we have much lower CO2 emissions because every liter or gallon of fuel that we save is going to be that much less CO2 emissions. And we have, a relatively low investment as compared to a battery system, again, because batteries are such an important big chunk of the total system costs usually. But you always reserve that flexibility for later. If you say the system works well for you, and at some point you do want to add some batteries, we'll see that in use case number 7, that of course gives you some benefits as well on top of this. So for use case number 6, I want to show you some of the energy flows in various running states. So this is the state during the day where you have typically sufficient PV power coming from the PV modules, and the generator is really only dictating the voltage and the frequency of the whole system and providing very, very little power, just like a few dozen watts if you have enough PV power, just to avoid any backfeeding into the generator. And that's the reason we also need that firmware, is because we're extremely fast now to make sure that if you suddenly turn off this load, that we're not backfeeding any significant power to the generator, which could damage it. To be clear, within 50 milliseconds, we've reduced that backflow to 0, which is well beyond anything typical grid-connected can do. Your typical grid-connected power systems will, even if you deactivate grid feed-in, will backfeed for hundreds of milliseconds, and in many cases 20 plus seconds into the grid before actually realizing that they're backfeeding and then reducing the power of the PV side. So that's very important when you're working with generators, that's a very quick process. In this next state, we have no PV power. So for example, during the night, or if there's snow on the PV panels or whatever, when we literally have no power coming from the PV side, then of course all of the power is being supplied by the generator, as was the case before the system was installed. So the requirements for this use case number 6, I don't want to get into too much detail because we don't have the time to, but these are just some recommendations from our side on some settings that you can make to get the most out of this and to have the best compatibility with generators, which may or may not give you a good clean sine wave to be able to handle those. Then use case number 7 is pretty much exactly the same thing, the only difference being that now you've added a battery. So again, we have a fuel saver scenario, we have a genset, but this time we've added a battery. So you can automatically start the generator with the integrated relay. Before, you could have done the same thing, except there's no reason to start or stop the generator because the generator is going to be running all the time if you have loads on all the time. In this case, you can actually turn off the generator for some of the time because your battery and PV side will take over. You don't need a generator at all for large portions of the day if the system is sized correctly. So your benefits here are, as before, you have significant generator fuel savings, probably higher than before because now you have this added storage ability with your battery. Now you even have fewer running hours of the generators because, again, you can switch off your generator entirely for several hours a day. You have less noise because, of course, during that time, the generator is not running at all. So then you have essentially a noiseless system during that time. And now you have much lower CO2 and other emissions because you're likely to save even more fuel and therefore emit less CO2. So same story as before. We have the various running states. This is during the day where we have a split scenario where we're requiring more power than is available from the PV side. So the generator has to feed in some power, and optionally, we can also supply power to the battery. Then we have the state where the generator is not running at all, because now, let's say it's the middle of the day, we have enough PV power, which means we don't need to take any power out of the battery. All of the PV power is being used directly by the AC loads, and the generator is completely switched off. So this is, of course, the best scenario for the user of the system, because this is where you're saving your fuel. This is where your generator is off, not causing any costs, both for fuel and for maintenance. And that's obviously going to be your goal, is to run as many hours as possible in this scenario. And when you have more PV power than you're using, then of course, some of that power will be put towards the battery to charge the battery for later, for when the sun sets, for example, so that you can only start the generator several hours later when you really need to. And of course, you can program how deep you want to discharge your battery before charging up, before starting your generator. Again, I don't have the time to go through all these requirements, but these are just some recommendations from our side if you want to use this scenario number 7. I'm going to have to speed up a little bit. So again, all the slides will be available for you after the session, or by tomorrow at the latest. So you can look these things up later. But I do want to give you an idea of how the prioritization works. There's 2 priority classes or levels. One is the AC output source priority, which is the title up here. That means, what power sources are we using to supply power to our loads? This has nothing to do with charging at the moment. This only has to do with what we use to supply power to our loads. So there's 3 modes here. The first one is USB, which stands for Utility Solar Battery. Utility could also be a genset, of course. The second one is SUB, which is Solar Utility Battery. And the last one is Solar Battery Utility, or SBU mode. So you can see these 3 modes being shown in the settings menu. And on the top, you can see which menu number this is. We have about 35 different settings we can set. So you can see this is the first one. This is obviously an important setting because this is basically defines a lot of the behavior of the AnyGrid. So in this first USB mode, again, utility is our first priority. So we're going to use the AC input power first, followed by solar and battery last. So again, this means AC source is being prioritized. And this makes sure that your battery is basically always sitting around full. And this is good in a sense, because it means that your battery is not being used to save cost. You'll see the other scenarios can use the battery to save PV power. But what's important is the battery is always full. So if the AC source fails, you can always be sure, regardless of whether it's night or day or PV is working or not, your battery at least is always full, so you have the maximum possible power reserve for your grid outage. SUB would be a scenario where you do want to use as much PV power as possible, but you still don't want to use your battery for solar. You just want to use your battery. You want to make sure it's sitting around fully charged for as long as possible, so that when the grid does fail, you have the full battery capacity at your disposal. So that's why in this case also the battery in the top 2 scenarios always last. The battery is only going to be tapped into if the other 2 sources fail or are not sufficiently powerful enough to power your loads at any point in time. And the last one is the SBU. Sorry, the order is switched around here, but SBU means Solar Battery Utility. So again, you're prioritizing solar first, but then you're also discharging your battery to a certain extent, and only using your AC source once your battery has reached a certain set point. And this is basically now your priority is no longer to keep your battery full at all times in case of a power outage, but rather to actively utilize your battery to further decrease your power cost. Because of course, if you're allowing the system to discharge your battery even when the grid is there, well, that means you can discharge your battery by say 50% during the night and then recharge during the day, and of course use solar power on the fly as well. And that just means that overall, throughout the year, you're going to be using a lot more solar power, even with the exact same solar array, simply because you're using the battery for buffering as well. And you can still freely choose how deeply you want to discharge your battery every day in your cycles so that you still have a certain power reserve for when the grid does fail. Now, the second priority setting is the battery charger source priority. So before we were talking about how to power our loads, now we're talking about how to charge our battery. And there, again, we have three different modes. The first one is solar first. And what this means is if PV is available, then we only want to charge with PV. But if there's no PV available at all, so during the night, or if you have snow-covered PV modules, then you can charge from the grid or from your AC source. You can independently select with how much current. The second setting is solar and utility, which just means both simultaneously. And then finally, we have only solar, which means that you're completely deactivating charging from the grid. Now, you can do that if you know that you're not going to get any snow, because even if you have a cloudy sky, for example, you're going to get, if you have like a 3, 4, 5 kilowatt system, you're going to get at least 100, 200 watts, even with very overcast skies, which is enough to power the inverter itself to cover its self-consumption. But if you have several days of snow, then you're literally getting zero from the PV side. And what can happen is the inverter can still slowly discharge your battery just to power itself. So in such a case where you might have snow, we recommend that you actually allow charging from the grid, but with just a very, very small charging current. So 2 amps on the battery side, so 2 times 48 volts for a 48 volt system, that's roughly 100 watts. That's all you're using to charge your battery, just to make sure that you're offsetting the self-consumption and adding a little bit more than that. Then we have the overload bypass. If you're in off-grid mode for some reason, because you want to, for example, because you're in SBU mode, remember SBU was solar battery utility in that order. If you're in that mode, that means that a lot of the day you're actually going to be running off-grid. Voluntarily, you're disconnected from the grid because you want to use just PV and battery as much as you can. Now, in such a case, remember all the power is flowing through the unit. So in such a case, let's say that you are using a 5 kilowatt inverter and your load has more than 5 kilowatts. If you do have a valid AC source, if you have a grid or if you have a genset that's running, you can tell the unit to switch to that AC source only temporarily to feed your load instead of switching off, because those are the only two options the inverter has. If it's being overpowered, it can only turn off to protect itself, or, and that's what the overload bypass permits, it can temporarily switch to grid mode, make sure that your peak is being served from the grid, and then switch back to off-grid mode or whatever mode it should normally be in as soon as you're consuming less than the nominal power. So again, most of the units can handle very roughly twice their nominal power in sourcing from the AC side. So you have a lot of headroom. Then we have both charging and discharging current limits. This is important if you're using undersized batteries, which obviously is not something one would ever recommend, but it's something that customers will ask for simply because batteries are so expensive. So especially in a scenario where you're not off-grid, where you are connected to a grid, people will tend to want to choose smaller batteries. And we're going to have to deal with that whether we like it or not. And we do that by reducing our charging current to adapt to the smaller battery, and also reducing our discharging current. Now, you might be wondering, how do I reduce my discharging current? Because if my load has 5 kilowatts, how can I reduce that? Well, I can't really. If I'm working in a grid environment, though, then just like in the bypass mode, I can temporarily switch to grid mode whenever I surpass, or yeah, whenever I get over that current discharge rating. So let's say, for example, that for the discharge current, I set it to 100 amps. That means that as soon as the discharge current exceeds 100 amps, the inverter will immediately switch to grid mode, serve the loads from the grid so as never to surpass the 100 amps. And as soon as the loads are below that threshold again, it will come back to off-grid mode. So like this, you can deal with small batteries. Then in our list of features, we also have the priority timers. And these basically allow you to override the charging priority and the AC output source priority. Remember, those were the two priorities we can set. That is our standard setting, whatever we set up in the main menu. But then we can decide to override that for a certain time during the day. So for example, if normally I want to make sure my battery is always full because I'm worried that I might have a power outage, but I know that, you know, there might be in the evening from, let's say, 6 p.m. to 8 p.m., that power might be a lot more expensive during that time because that's a typical peak evening peak scenario. Then I can still override the AnyGrid to say that during that time, I want to use the battery instead of the grid, for example, because I'm still not willing to pay that higher price for power. So this is just a temporary override setting, and you can set from what time to what time every day you want to override your standard setting. Then we have this battery-free mode, where, and this one I think again is very interesting because it just gives us a lot more flexibility in the use cases. Here, basically, we're always taking a very small amount of power from the AC source to make sure we're not backfeeding anything if we're not allowed to, unless, of course, we've activated grid feed-in. And then we still use all the PV power we can to power our loads. Grid feed-in should be obvious what we're doing here. It means that we're basically never reducing power from the PV side, because if we have too much power, if your battery's full and your AC loads are basically taking all they can and you still have some extra power left over, then we can shift that power to the grid. To enable that, like I mentioned, you will have to enter a PIN, and you can obtain that from Phocos, because we of course want to avoid people activating this functionality if it's not legal in their area. Then one of the last features I want to present today, there's of course a lot more, but again, time is running. I think we only have like half an hour left, and there's a lot to get through, and I won't be able to cover everything in detail. But we do have the Phocos Link mobile Bluetooth app, which you can download both for Android and iOS devices, and that will allow you to see all your current values from your AnyGrid inverter in real time, basically. Now let's look at some of the benefits. If we compare the AnyGrid to a classic off-grid system, for example, where to get the same functionality, you need to buy an MPPT charge controller, you need to buy an inverter, you need to handle the switching between off-grid and on-grid mode, so you need some really fast switchover and synchronization system. You need a grid charger as well, and then you need to get all of those devices to talk to each other. That's what we're comparing against, and of course the AnyGrid is a fraction of the cost, literally much, much lower. We're talking half, a quarter, maybe even of the cost compared to buying all these components in the specific power class individually. Then we have a much, much easier installation because of course we have a lot less wiring and therefore lower complexity, and we don't have communication between devices going on. We have this automatic synchronization to the AC source. Basically, as soon as an AC source is available, if it's within the limits of voltage and frequency, the inverter, even if it's in off-grid mode, will automatically synchronize, because that's the only way you can switch so quickly. You need to be synchronized beforehand to then switch very quickly, let's say in a bypass scenario where you have no time to react. Your load is larger than what your inverter can deliver, so you immediately need to switch to the grid. And the way we achieve that is by synchronizing beforehand. Then this definition of energy source and charging priorities is really what defines these various use cases and how you control the unit. We have less points of failure because of the much reduced wiring requirements. All the system data is on a single device. So for your data logger, you can get your PV data, your AC data, all of that on a single device. You don't have to worry about monitoring multiple units. And it really is a set and forget system. Once you've set it up with those initial, there's 35 parameters in total, of which you probably only need to touch maybe 6. Then the system will simply take care of itself. Then more benefits, of course, are in the actual Phocos ecosystem itself, which is that we're in communication with various battery manufacturers and testing, and we have support for Pylon Tech batteries out of the box with BMS communication. Again, we're in contact with other providers as well. We have the Phocos Link mobile app, which we've developed entirely in-house as well. We have very extensive documentation, training such as this, and a very extensive manual as well. We have system sizing help from our team, and of course we have expertise for the last 19, almost 20 years in the field of PV and off-grid. Another very important benefit is the high PV voltage. Now, for every unit is designed so that you need only 1 or 2 PV strings. And if we compare that to a classic MPPT, which typically has 150 volt maximum for a 48 volt system, well, that typically means that you can do only 3 modules, maybe even 2 just in series. It means that you have 5, maybe 6, maybe even 7 strings for a larger system, which means you need a combiner box. A combiner box will set you back $150, $200 easily. It needs to have a high IP rating. You need string fuses or diodes, and obviously you have a whole bunch of cables to handle. Now with the AnyGrid, we're working with much, much higher voltages. For the 120 volt devices, we can go up to 250 volts on the PV side. With the 230 volt devices, it's even 450 volts. So any device you buy, you can be sure that 1 or 2 strings are sufficient for the PV side. And what that basically means is you need smaller cable cross sections, which will save you cost and space. You don't need the combiner box. At most, if you have 2 strings, you need these very cheap Y connectors, which cost maybe $10 a piece. You don't need string fuses or string diodes. You have fewer cables going into the building because here you basically have the choice. Do you want to put the combiner box on the roof? It means that it needs to be weatherproofed. And then you have 2 thick cables going down to the charge controller. But with the AnyGrid, you just have 2 thinner cables going inside. You don't need a combiner box at all. So again, we can handle 450 volt open circuit for the 230 volt models and 250 volts for the 120 volt models. Now here I give you a few examples. Again, time is running out, so I can't really go into a lot of detail, but here's one example with a classic 72 cell PV panel, the way they're used a lot in the Americas, where we have about 46 volt open circuit as a PV voltage per module and 340 watt peak we're assuming here. And what that means is for the 3 kilowatt unit, you can, with 2 strings, you can put 3.4 kilowatt peak of PV power, again, with no combiner box required and no string fuses and all the other things that I've just mentioned. For the 5 kilowatt 120 volt unit, we even have the 2 MPP trackers. So of course that gives you another whole raft of advantages compared to having just 1 tracker. A lot of them may be obvious, some may not be. Again, we have 250 volt open circuit per MPPT, so easily 100 volts more than most of the competition would. We have a higher tolerance for partial shading as compared to single MPP trackers. What that means is if you have like leaves or something on some PV modules, then you will lose less power in a system with 2 MPP trackers as compared to a system with 1 MPP tracker. You can also use this in more complex roof shapes. So you might have an east-west roof instead of a south-facing surface, and you may have a completely different solar irradiation on one side than you might on the other. You can even mix PV panel types. You might have thin film on one side and crystalline solar panels on the other side, and like that you can use the relative advantages of two different types of PV panels. And again, no combiner box is required. So in this example, we're using 60 cell modules, which typically have about 38 volt open circuit and 270 watt peak plus minus, let's say 15 watts. And in this example, we have 20 modules connected, which will give you up to 5.4 kilowatts of PV power potential, of which 4,800 watts are truly usable at any point. Now, the extensibility, I think, is extremely important for these devices as well, because you saw we have 3 and 5 kilowatt units, but you may want more than that. So any of these models can be hooked up to 8 further units for a total of 9 units per system of synchronized inverters. They must always be identical, so you can't mix 3 and 5 kilowatt units, but this gives you even more flexibility because it just means that you can set up a single AnyGrid, and you might realize later that you want to add some PV power, or that you have bigger loads than expected, and you can just hook up a second AnyGrid and have those two running in parallel, or you'll see in 3-phase or split-phase configuration, however you like. Now, all of the connectivity requirements between the units, all the cables that you need, the interfaces are all included on the units. So every AnyGrid you buy already has the parallel cables required for these multi-unit systems in the package. You don't need to purchase anything separately. So these, you saw those in the beginning. These 4 connectors are what's needed to connect the units to each other, to make sure that they're synchronized, to make sure that they speak to each other, have the same parameters, etc. These left green sockets are only required if you have more than 1 unit on a same phase. And I'll show you a couple examples. Here, for example, we have 5 units on a single phase in parallel. Each one must have its own PV array. They must always be separate, which is, of course, also a benefit because it means that in this system you have 5 MPP trackers. They must always be connected to the same battery as well. And then, of course, we have the AC source, where all the units are connected in parallel, and our loads, where all the units are connected in parallel. Now, if you're using 5 kilowatt units, then of course this means now we have 25 kilowatts of nominal PV power, of nominal AC power. PV power is slightly lower than that. You see these are the wirings on the bottom. If I go back one slide, it's this part basically that we're showing in the diagram. The green cables are the ones that we need if we have more than 1 unit per phase, which we do. All units are on the same phase, so they must all have the green cables. And then the gray or black cables are the communication cables, which are always required for multi-unit systems. Now we contrast that to a different system here, a bigger system where we have 9 units interconnected. The first 7 units are on a single phase. This is a 3-phase system. And the second last and last units are on phase 2 and 3. So what that means is these last 2 units, there's only 1 unit per phase. And you may notice down here that these 2 last units do not have the green connection cables because now we just have 1 unit per phase. That's the main difference we're trying to show here. And of course, you can also see a nice side effect is we can build up asymmetrical phases. We can put a lot more power on phase 1 or phase 2 or phase 3 than the other phases.
For more videos and information, go to www.phocos.com. Phocos, making reliable energy access possible. Anywhere, anytime, any grid.